Hello everyone, I welcome you to the course UAV Design. In today's lecture, we are going to see about the design process of unmanned air vehicles and systems engineering approach to build an UAV. UAV design is an iterative process involving synthesis, analysis and evaluation. Synthesis is the creative process of combining known elements into new and useful configurations. Analysis is the predicting the performance or behavior of a design. Evaluation is assessing the predicted performance of a feasible design candidates to identify the deficiencies. UAV design requires both integration and iteration. It's an iterative process. There is a strong interrelationship between synthesis, analysis, and evaluation. The process involves continuous refinement to optimize the UAV's performance. There are basically two main groups of design activities. The first one, problem solving through mathematical calculation, which involves engineering equations, computational modelings, and simulations. For example, estimating the aerodynamic performance, calculating structural integrity, and analyzing it. There is a second method, choosing a preferred design among alternatives from the historical trends, available data. Based on the performance, metrics, cost, feasibility, and mission requirements from the historical data, we choose our preferred design. We conduct trade-off studies to balance the multiple design factors. It includes basically the performance, L by D, range, endurance, performance matrix. These all things we include in trade-off matrix. The full range of attributes and characteristics of an engineered UAV system is important as for both producers are the engineers who are working on that, and the customers are the end users of UAV. They are design dependent parameters, the attributes which inherent in the design, predict or estimated. Primary responsibility for the UAV producer are weight, how it affects the performance and endurance. Design life. Do the UAV which is designed will meet the expected operational lifespan? Liability. Do the UAV designed has a probability of successful operations? Do the UAV has a producibility or its ease of manufacturing? Do it has ease of servicing and repairs? Do it is maintainable at the minimum cost? These are the basic responsibilities which has to be taken care by the UAV producers. Disposability. Environmental impact of decommissioning. Once the unmanned air vehicle completes its technical life, then what is the procedure for disposal? Even that has to be considered at the time of designing these unmanned air vehicles. And apart from design dependent, we have few design independent parameters such as external factors influencing the design evaluation, which is dependent on production and operating environment. Examples: fuel cost per gallon, interest rates, labor rates, material cost per pound. This is the basically UAV design groups where a chief designer will be the in charge for the entire UAV design, and under him there will be experts in the department of structural who will be taking care of structural components and structural integrity. Then aerodynamic designer will be there, aerodynamics team will be there which will be working on streamlining the body. Payloads department will be there. It will ensure what kind of payloads like equipments, devices, sensors, what kind of payloads are to be incorporated depending upon the requirements. Then propulsion system, depending upon the mission, what is the range of the mission, what is the endurance of the mission, the propulsion system will be chosen. Propulsion system will be chosen from the existing engines. For example, the design requires a turbofan engine for its mission to carry for 7 days. Then an existing turbofan engines will be chosen. No engine will not be designed separately for this UAV. UAVs will be designed based on the engine's availability. The UAV design will be surrounding its design through the engines which are available. No engines will be separately designed for it, whether it is electric propulsion or it is jet propulsion. Then autopilot. There will be a special team which will be working on this autopilot mechanisms. They will be taking care of the devices, sensors, transponders, whatever has to be installed in the fuselage part of the UAV. They'll make a data of it and they'll submit it to the chief designer. Then ground control station, who will be monitoring from the ground roll to the touchdown of the UAV. Launch and recovery. There are different types of launches which UAV can go. Basically, we have hand launch. So, or we can go with caterpillar takeoff or ground roll and then takeoff. These are the 3 launches which generally UAV will be having. And apart from that, when it lands, recovery is nothing but landing of UAV. A few unmanned air vehicle will have Bailey landings, and few unmanned air vehicles will have a proper touchdown, then ground roll, and then they'll come to velocity 0, where it is completely grounded. Apart from these teams, a special team will be there which will be working on mission design. They'll be completely designing the objective of the unmanned air vehicle, like what will be the ground roll, takeoff, climb, cruise, then descend and land, ground roll, and velocity equals to 0, where it is grounded completely. And support systems. What kind of support systems are required for a UAV? Like if it is a caterpillar takeoff, what kind of launching system is needed there? That will be taken care by this team. If it is a hand launch, who will be holding it and what angle of attack it has to be holded and how far it has to be pushed. Then landing gears, depending upon the mission requirements, they will be choosing the landing gear. They'll have nose landing gear, main landing gear, or some UAVs will have a tail dragger type which will be looking like this. Suppose this is your unmanned air vehicle, so they'll have a tail dragger here. Or if it is a basic unmanned air vehicle, so it will have 2 main landing gears at the front, and it will have 1 supporting rear landing gear. And if we see it in the front view, it will look like, it will be looking like this. This is the landing gear mechanism what we have. And in general, we have tricycle landing gear, bicycle landing gears, and buggy landing gears. But here we'll be using tricycle landing gears in unmanned air vehicles. Then we have communication systems like transponders, radios, radar, antenna. These all will be installed. Suppose this is your unmanned air vehicle, for example. So it all will be installed here. This radar is placed as much as possible. It will be located here so that it have a clear sight for the communication with respect to the radar. And rest all the landing gears, after deflected, it will be placed in these boxes. Here you will have your autopilot system. Here you will have your communication systems. And generally this will have your main engine, turbofan engine. Basically here we'll have the turbofan engines. Systems engineering approach. UAV systems are complex interdisciplinary engineering projects. System engineering methodologies help manage the risks and cost. Here it is interdisciplinary because it includes the areas like not only design, but it includes structure, it includes communications, navigation, programmings. Programming is done, radio programming, and even a few unmanned air vehicles are integrating the technologies of AI and ML for autonomous flying. Right. So it's an interdisciplinary domain. So multiple areas are there and multiple engineers, multiple expertise people are involved in designing an unmanned air vehicle. UAV conceptual design integrates multiple disciplines such as aerodynamics, structures, propulsions, and control systems. Configuration design requires knowledge of design principles and systems engineering approaches. It begins with defining requirements and extends through functional analysis and allocation, design synthesis and evaluation, validation. A system approach ensures optimization and integration with operational needs. Life cycle oriented design minimizes undesirable side effects and improves efficiency. UAVs consist of multiple subsystems. The first one, flight control subsystem, power transmission subsystem, fuel subsystems, in case of it is a jet engine based. Then we have structures, propulsion, aerodynamics, landing gear. These subsystems transform an aerodynamically shaped structure into a functional UAV. This flight control system here, it will completely work on the performance of the unmanned air vehicle. Then fuel subsystems, this will help in supplying the fuel to the turbofan engines which are placed. Structure plays an important role here because we need to have a proper structure where in the fuselage we can accommodate the payloads. Propulsion system, it is again basically depends on the objective of an unmanned air vehicle. For example, if it is for 1 to 2 hours, right, depending upon this 1 to 2 hours, we can go with electric propulsion, which is battery based, batteries and motors, or we can go with small jet engines, turbofan engines basically. Nowadays for hobbies, many people are using even piston engines for 20 to 25 minutes of endurance period. For the endurance period of 20 to 25 minutes, many people are using even small piston engines. Then landing gear, these landing gears are designed for unmanned air vehicle to ensure that when it touches down, when this unmanned air vehicle is touching down this ground here, when it impacts here, it has to be designed such that the impact load which is generated from here shouldn't affect the structure of the unmanned air vehicle. It should have a mechanism to overcome these impact. This mechanism is called shock absorber. In conceptual and preliminary design phases, subsystems must be defined and analyzed. UAVs are interrelated systems with defined objectives such as safety, cost-effective flight. Key subsystems include UAV platforms, terminals, ground support, equipment, and control stations. UAV life cycle must be considered covering design and development, manufacturing, maintenance and support, phase out and disposal. These are the areas which has to be considered, and this is the life cycle of an UAV. Life cycle engineering must be incorporated early in the design process. UAV producers must ensure product competitiveness in a global market. Systems engineering aligns mission expectations with cost effectiveness. Competitive UAV design balance the performance with affordability, reliability, and supportability. Traditional UAV design focuses on minimizing maximum takeoff weight. Traditionally, we have to, as a designer, we'll ensure that as much as possible, we'll minimize this M2AW. And in this maximum takeoff weight, it will include the weight of the crew, weight of the payload, weight of the empty structure, weight of the fuel. When we talk about unmanned air vehicles, here we don't have crew. So this will be included in, this will be combined with empty weight. Instead of crew, we have our payloads which are accommodated in the fuselage. It will be payload plus empty weight plus fuel weight. And in case if it is turbofan, if it is not turbofan engines, it is based on the batteries and motors, then the maximum takeoff weight will include payload plus empty weight. This fuel weight will be omitted in the case of it is electric motors. Multidisciplinary design optimization ensures an optimal UAV configuration. The MDO framework involves defining design parameters, constraints, and objectives, evaluating relationships between design options and requirements, applying systems engineering principles, developing an optimized design methodology. UAV design must align with performance requirements, stability and control requirements, operational outcomes such as safety, producibility, maintainability, and disposal. Integrated design ensures UAV compatibility with physical and functional needs. Continuous evaluation is crucial for refining UAV design. Key evaluation phases are identifying customer needs, system objectives. These customer needs are actually termed as requirements. Again, these requirements will be based upon the clients. These requirements will be submitted in the form of request for proposal for an entirely new design, and if existing unmanned air vehicles are available, then RFAs are given by the manufacturers and producers. Request for approval. This is request for proposal, and this is for request for available data. Conducting feasibility analysis, determining system requirements, designing and developing system components. These are the areas where major evaluation takes place. Feasibility analysis is how it gonna function, how it gonna respond to the requirements, and based upon the requirements, what performance it's gonna give. Then determining system requirements. Again, this is dependent on the performance. Performance is completely based on these requirements. Then designing and developing system components. Prototyping and validation. This is the final phase of our UAV design, where after the designing, a prototype model is being tested at various conditions in the wind tunnel. Like like how it responds to the ambient conditions. A wind tunnel test is considered. A wind tunnel test has been considered to ensure this will create the boundary conditions of the objective. This will create the boundary conditions of the objective, such as, suppose I want to fly this UAV at 30,000 feet altitude. So I'll be creating that atmosphere in this test section. A prototype model will be made, created and tested for 30,000 feet altitude, which will be done in this phase. Once these results are out, these results will be compared with the CFD results, and then this scaled down model can be tested for 30,000 feet altitude, the actual altitude, and the validation is been done. So for validation, they'll compare the experimental data, computational data, based on these experimental and computational data, the validation is been done for any design. UAV design phases, basically there are 4 major phases of unmanned air vehicle design. The first one is conceptual design. Here in this conceptual design, an initial concept is developed based upon decision making and selection techniques. During this conceptual design phase, a rough sketch will be drawn, like suppose how my unmanned air vehicle will look like. It's a rough sketch. It will have a wing, it will have a canard, it will have a conventional tail with it will have a conventional tail, and it will have an elevator here, right? So this is this will give you a rough sketch how it looks like. It will give you the thought process, like this is the design and this is going to look like. These sketches are rough sketches to just give the idea of the concept. Once the conceptual design phase is crossed, when we enter the preliminary design phase, then the basic calculations and analysis refine the concept, and if there is a change in the primary control surfaces of these unmanned air vehicles, if it is not required, this can be removed. It's not mandatory that it will be removed in the preliminary design phase. Depending upon the outcomes, if our outcomes are very good without these primary control surfaces, then it's better to remove it because the weight will be minimized. Then we have the third phase, which is detailed design. It is a finalization of technical parameters, including geometry of key components. There are many examples existing in the literature which shows that an aircraft is designed with, initially which was designed with a canard and a wing. When it came to the final fabrication model, prototype model for testing, the canards were removed. There was only a wing with a proper tail section. And the last phase is test and evaluation, where we validate the design through simulations and real world testing. Simulations we do using computational modeling, and real world testing we do using prototype testing in the wind tunnel with scale down model. Correct? Scale down model. Then again we have the concept of flow similarities and dynamic similarities. Based on this, then we'll using these similarity principles, we conclude our testing for full scale model. Conclusion. In today's lecture, we have seen UAV design follows an iterative loop of synthesis, analysis and evaluation. It requires balancing design dependent and design independent parameters. Selection of UAV design is based on quantifiable objectives and constraints. It's a continuous improvement through iteration and integration, which leads to an optimal UAV system. UAV systems engineering integrates multiple disciplines for optimized design. Life cycle of the engineering ensures long-term feasibility and sustainability. Multidisciplinary design optimization enhances UAV competitiveness. Continuous evaluation and refinement are essential for successful unmanned air vehicle development. This is the reference which is used for this lecture. Thank you.